Record on this computer. Here we go. We're going to record. Hello, kids. We are going to be doing Atomic Theory, class number 1, notes number 1 to 25. You should get your notes out. You're going to need a reference table as well. Open up to the periodic table. We're going to need that soon. We're going to finally do some chemistry, like legit chemistry. No more measuring, no more numbers, no more significant figures. We're going to look at what is an atom? How is it built? What are the parts? Where are the parts? What is a periodic table? And what are all those numbers? And we're going to start looking at all this stuff. And we're going to look at something called electron orbitals, which are actually pretty cool too. So here we go. In the notes, all atoms are made up of 3 parts. They're called subatomic because sub means less than or smaller than. So there are 3 main or basic parts to an atom. And you know what they are. Okay, I'm not even going to tease you. They're called the proton, the neutron, and the electron. Every atom has protons, neutrons, and electrons. Actually, I guess we could argue that hydrogen almost never has a neutron, but all atoms have protons, neutrons, and electrons. So we'll just try not to get involved in too many details quite yet, but proton, neutron, and electron. Now, each of these particles, pretty dang small. I mean, atoms are ridiculously small. These are even smaller. And they have charges. These particles are charged. And the charges for proton is positive. The neutron is neutral. It has a 0 charge. And the electron is negative. Now, we don't get too involved in the physics of how positive or how negative, but it is important to know that the charge of a proton and the charge of an electron are equal and opposite. So if you have an atom that has 1 proton and 1 electron, it is perfectly neutral. So how positive, how negative, this becomes very complex as to measuring that, but equal and opposite. So if you have an atom with 2 protons and 2 electrons, also is very neutral, completely neutral, exactly neutral. Now, rather than writing proton, neutron, electron, students don't like to use so much ink, so we use these symbols. It's a lowercase p with a plus sign, superscript plus. The neutron is a lowercase n with a superscript neutral 0. That's like a degree sign, but it means, in this case, 0 or no charge. And then the lowercase e for electron with a little negative charge. And we can use these symbols. It makes it easier and quicker, right? Well, we'll be talking about protons, neutrons, and electrons. There's no other, they don't mean anything else. We're not going to get fooled by this. Now, everything that's matter takes up space and has mass. Now, the space taken up by a proton, a neutron, or electron is fantastically small. I mean, ridiculously small. And protons and neutrons are terribly tiny. Electrons are gigantically smaller. Protons and neutrons are a little bigger than electrons. I mean, well, they're so small. They're all so small. Now, how much do they weigh? What is their mass? Now, in high school, we say 1 atomic mass unit. A proton equals 1 AMU, or atomic mass unit. It's a ridiculously small unit of mass that's there's a mathematical number of grams with a lot of zeros in the front of the decimal. It's a very, very small number of grams. But there's a legitimate mass. We're not going to ever do math about it. We're just going to say, hey, equal to 1 AMU. Neutrons also are 1 AMU. Now, this is a really weird thing. Electrons in high school, casual, we're friends. We're just getting to know chemistry. Electrons have no mass, but that's not really true. They have a very, very small mass, but it doesn't make much difference to basic chemists. We're learning basic conceptual chemistry. The mass of an electron is a fabulously important number, but not to us, okay? It's just not that important. Now, where are these parts? Now, there's 2 parts to an atom. Basically, there's the middle part. You know what the word is, starts with the letter N. It's called the nucleus. And in the nucleus is the protons and the neutrons. And again, the protons and the neutrons each weigh 1 AMU each. So all of the mass, so to speak, all of the mass is in the nucleus. And the electrons are flying around on the outside, actually pretty far away compared to the size of an atom. They're not too close. It's weird. Electrons are kind of far from the nucleus, but they are in kind of an orbit, or orbital we call it now. It's not called an orbit anymore, but they fly around and they don't get away. They are associated with specific nucleus, and the electrons belong to a certain nucleus, and they fly around. Technically, the electrons have no mass in high school, but all the mass is in the nucleus, but in reality, there is a little tiny bit of mass flying around with the electrons. Now, isn't this a cool little diagram here on the bottom? Look at it zipping around. The mass of the electron is not zero. Technically, that's approximately correct. 1/1750th the mass of a proton or the mass of a neutron. We're going to disregard it. We're going to call it zero. But in all honesty, it's an important number. The nucleus is said to be very small and very dense, squished tight together. And the electrons are flying, relatively speaking, far away. Now, we've seen cartoons like this before. This is a really cool cartoon. I stole this from the internet. I'm sure you could find it somewhere. There seems to be an orange nucleus and 3 little orbits there with 3 little electrons, a red one, a green one, and a blue one zipping around. This is not realistic. Atoms don't really look like this. It's a cartoon. But from this, we could learn some really cool stuff. If you're an atom, of course, you have a nucleus, and in the nucleus are your protons and neutrons, and we can't really see them. There's just a gold ball. It looks like the number 1 ball on a pool table, which is kind of a gold color. But if an atom has 3 electrons, there's only 1 atom in the world that has 3 electrons, atom number 3 on the periodic table. And if we look at the periodic table, atom number 3 is Li, or lithium. Now, if it's lithium and it has 3 electrons, because only lithium has only 3 electrons, the positive part of the atom, the protons, has to equal the negative part. And that would mean it has to have 3 electrons and 3 protons, because the positives equal the negatives. Lithium atoms are neutral. How cool is that? Now, I know there's 4 neutrons. I'm not going to tell you how I know that yet. You can think about it. Look at the numbers in the boxes. See if you can figure that out. But we'll get to that in a couple minutes. But this would be a good cartoon for lithium, but it doesn't really look like that. Lithium atoms don't look quite like that. And those electrons are way too organized and cute. AMU stands for atomic mass unit. It's a super small, tiny bit of mass. There's an actual number for you there with 3 significant figures. We're never, ever going to do math about this. We're just going to talk about atomic mass units. We will never convert from atomic mass units to grams or grams to atomic mass units. Never. Don't worry about it. In high school, a proton is equal to 1 AMU. In reality, neutrons are a little bit bigger, but who cares? 1 AMU each, close enough. We're doing simple chemistry. We're beginning to get to know the atoms on the periodic table. There's a lot of details. We're going to gloss over some of those details for a while. We have to just kind of get our feet wet and see what all these numbers mean and not worry about everything. We'll get to everything else, but let's start simple, and then we'll get to the details a little later. In high school, the mass of the electron is so much smaller than the mass of a proton or the mass of a neutron. We're just going to skip it. It's not 0. But in high school, doesn't matter. We're going to call it 0. We're going to be friendly about it, but it certainly is not 0. It's an important number, but not in high school Regents Chem. In Regents Chem, no mass. Now, on the key is the key of the periodic table. You should have this out. There's a bunch of numbers. This happens to be the blow up or the exploded view of carbon. Carbon is an atom on the periodic table. They just pick carbon. C because, I don't know, maybe because C stands for Charlie, or C stands for chocolate chip cookie. Those are 2 really good things. Could pick any atom. Now, in this slide, we have an atomic mass in the top left, right? 12.011. That's just a number. There's a unit, AMU, but we don't write it because it's a little box. That's the mass. The atomic number is 6. Carbon is the 6th atom. There's 118 atoms. Carbon is the 6th one. Now, underneath that is something called the electron configuration. We haven't talked about that yet. The electrons are not just flying around. They actually are in a pattern, and each of the orbitals is numbered, 1, 2, 3, 4, 5, 6, 7. And in the first orbital, Carbon has 2 electrons, and in the second orbital, it has 4 electrons for a total of 6 electrons. They're not just zooming around. They're in a little bit of an order. So it's number 6. That means it has 6 electrons. Carbon is atom number 6. That also means it's got 6 protons because the positives equal the negatives. 6 positives, 6 negatives. Where are those flying around negative electrons? 2 of them are in the first orbital and 4 of them are in the second orbital. Now, there are some other numbers. You can see them in the top right-hand corner. Those are called selected oxidation states. That means there are other oxidation states, but these are the ones the state of New York says we got to pay attention to. Well, let's not talk about them today. We got enough numbers to play with. We'll be busy for a while. Those other numbers, the selected oxidation states, are very important, but they're not very important today. We'll get to them, I promise. They're really cool. I like them, but not today. Now, we are going to look at the mass numbers. The mass number for carbon is 12.011 AMUs. We're going to round it to the nearest whole number. But they're all decimals, right? Some of the bigger ones are not. We'll talk about that also. We're going to round them to the nearest whole number. They're not whole numbers. We're going to round them to the nearest whole number. And again, we're going to get to some of those details another time. Now, the mass number, the atomic mass number, how much does the atom weigh? What's the mass of the atom? Is equal to the mass of the protons, how many protons, plus the mass of the neutrons, how many neutrons. So the mass of Mercury's number 80, my favorite element. It's the best element, which is a qualitative measure, but it's true. The mass of Mercury is 200.59. We round that to 201 AMUs. So that means it's got a total of 201 protons plus neutrons. Protons and neutrons. All of the nucleus is in the center of the atom. All of the protons in the nucleus and all the neutrons in the nucleus make up all the mass of the atom. The electrons flying around the outside, and they have no mass. Now, Mercury has a mass of 201 protons and neutrons all together. The mass is 201. How many are just neutrons? How do we figure this out? Well, the numbers on the periodic table are going to show us. We're going to do this for Mercury and a few more atoms, and you really should be able to learn to do this for all the atoms. Now, watch what we're going to do. The mass of Mercury, rounded to the nearest whole number, is 201 AMUs. That's the mass of the neutrons and the protons. So if we have the neutrons and the protons and neutrons all together, and it's 201, and I take 80 protons away. How do I know there's 80 protons? It's number 80. There's 80 electrons and 80 protons. So if there's 201 total protons and neutrons, take away the protons, how many neutrons are left? 121. Mercury is my favorite element. And I tease you that you need a favorite element. I know, I remember, I don't have to do the math. The atomic mass of Mercury is 201 AMUs. It's got 80 protons and 121 neutrons, and I remember that. And you know what's really convenient? When somebody says, hey, Charlie Abuso, how many neutrons are in, I don't know, an iron atom? I have to figure out how to do that. But I can do that because if I know that Mercury has a mass of 201, that's a number on the periodic table. And I take 80 protons away, and that's a number on the periodic table. The missing number, 201 minus 80, is the number of neutrons. I could do that for every single atom on the periodic table. So once you learn how to do this, pick yourself a favorite element. And then you'll memorize 3 numbers: the mass, the number of protons, and the number of neutrons. And then you can use this, what you remember for your favorite atom, to do on all the other atoms. Tin is number 50, SN. Tin Man is a character in the best movie ever made called The Wizard of Oz. So an atom of tin, if we look it up, number 50, it's right here. It has a mass of 118.71. We call that 119. 119 is the total number of protons and neutrons in the nucleus. And if we take away the atomic number, the number of protons, that's 50. we're going to be left over with just neutrons. And how do we do that? The mass is 119 minus 50 protons. That means there's 69 neutrons. Tin has 50 protons, 50 electrons, because the positives equal the negatives, and 69 neutrons. Now, it's a little tricky, right? Because the proton number equals the electron number because positives equal negatives. The mass number is the protons and the neutrons. They have mass. Take away the protons, that equals the neutrons. So there's two things. Protons equal electrons, and the mass, take away the protons, equals the neutrons. You have to kind of get this in your head, which is which. All atoms are electrically neutral. I said this before. The number of protons equals the number of electrons. The positives equals the negatives always. Every single atom, there's a perfect balance between positive and negative. Every atom on the periodic table is neutral, electrically neutral. Not positively charged, not negatively charged, neutrally charged. The atomic number is the number of electrons. The atomic number is the number of protons. It's always the same. And the mass, I got the whole nucleus in my hand, the protons and the neutrons. That's protons plus neutrons gives us the mass. Now, how many protons, neutrons, and electrons are in the element called indium? Indium is In. And indium is right next to tin. It's number 49. Do it. I'm going to have a sip of seltzer. You do this. Don't wait for me. You do this. Write the mass number down. The mass number rounds to a nearest whole number, 115. The atomic number is 49, so 115 protons and neutrons. Take away 49 protons, leaves the number of neutrons. Look how easy this math is. It has 66 neutrons. Indium's got 49 protons and 49 electrons because positives equal negatives. And the mass, 115, take away 49, gives us the number of neutrons, in this case 66. Two more atoms in a row, niobium and barium. Niobium and barium. And this reminds me of a chemistry joke, so while you're doing this, I'm going to tell you a joke. But you need to look this up. Niobium is element number 41. Barium is element number 56. There are three elements on the periodic table that are called the medical elements. And element number 2 is helium. And curium is named after Marie Curie, another element, and barium. So why are helium, curium, and barium called the medical elements? Well, that's because if doctors can't helium or curium, then they're going to have to barium after all. I know, it's a bad joke. There's a lot of bad jokes in chemistry. Niobium, 92.9064. That's a mass of 93. Take away 41 protons. And barium has got a mass of 137. Take away 56 protons. And look at this. It's easy to skip through this and say, I'm just going to copy it or I don't care. This is not difficult. The periodic table's got a bunch of numbers on it. And one of the first and coolest things you can figure out is the number of neutrons in any atom. Normal people don't care how many neutrons are in an atom, but you're a chemistry student. And I don't want to call it a trick, but the trick to this is just to know what some of these numbers mean. The mass number is the protons plus the neutrons. The atomic number is the number of protons. It's also the number of electrons because positives equal negatives. The nucleus has all the protons and neutrons, all the mass in the nucleus. And if you take away the protons, you always know the number of neutrons. You should be able to do this now for every atom on the periodic table. This is an important, basic understanding of what's on the periodic table. This information is available for all the atoms on the periodic table. Now, we can write symbols in a lot of ways. If we look at calcium is atom number 20, Ca for Charlie Arbuso, calcium. You can write some basic information in a formal way that makes it so that all the information you need to figure this whole proton, neutron, electron thing out is right in front of you. We round the mass to the nearest whole number. The mass of calcium is 40.08. We round it to 40. And the atomic number is number 20. That means it's got 20 protons and 20 electrons. And if we write it like this, the mass number on top, the atomic number on bottom, those are little numbers, a superscript and a subscript together, followed by the symbol, capital C, lowercase second letter, lowercase a. Now I'm asking you to write the formal symbols like this, just like the one on top, for mercury, chlorine, and copper. Mercury is atom number 80. Chlorine is atom number 17. And copper is atom number 29. Go. I'll have some more seltzer. Today's class brought to you by Dragon Fruit Berry Seltzer by Wegmans. Fabulous stuff. I'm really enjoying it. Look at what we got. Mercury has an atomic mass of 201 AMUs when we round it to nearest whole number. It's got 80 protons. It also has 80 electrons. Chlorine has an atomic mass of 35 AMUs. It's got 17 protons. And copper, 64, is the mass of copper, and it has 29 protons. So from this, you could figure out, well, if the mass of copper is 64 and you take away 29 protons, how many neutrons? This is a good thing. Also, copper reminds me of a really good song. There's a song by the Beatles, and I understand the Beatles were a long time ago, and they've not been around, and two of the members have actually passed away by now, and Paul McCartney is very old, and Ringo Starr actually played in the arena a couple of years ago, and I went to see him. It was one of the best nights of my life. Took my son, and we sang songs from the 60s with Ringo Starr. It was so cool. But one of my favorite Beatles songs is When I'm 64. And I'm going to be 60 years old soon. And I heard this song when I was a child. I'm sure I heard it before I even knew what it was. But I've been singing it my whole life. The song came out in, I think, 1967, 66 maybe. I was 6 or 7 years old. So my entire life, I've been singing this song, thinking one day I might actually be 64 years old. And it's coming. I highly recommend you write this down. When I'm 64 by the Beatles. And soon, we're up to 17 now. We're only going to 25. Soon you go to YouTube and you watch that song. It is one of my favorites. I love that. Okay. I'm silly sometimes. Okay, electrons, they don't just fly around. They don't just zoom around like that cartoon we saw before. Electrons stay in what we call orbitals. And the orbitals are also called energy levels. And there's a pattern, an organization to them that took a long time for scientists to figure out. And we got to learn a little bit about it. It's not hard, but it's not just random, and we got to pay a little attention. Now, the electron orbitals that's closer to the nucleus, the smaller orbitals, physically smaller and closer, those are called lower energy levels. So the electrons in the first orbital are going to have less energy. They're going to be less energetic than the electrons in the second orbital. The electrons in the second orbital have less energy than electrons that might be in the third or the fourth orbital. And there's a total, you could have up to 7 orbitals in an atom. The bigger atoms have more orbitals. The smaller atoms have less. They usually almost always have only the amount they need. Rarely would they have extra or be out of order. There's always quirks, but generally the electrons fill up the orbitals. They fill up the first one before they start the second. They fill up the second one before they start the third, and etc. But closer to the nucleus are lower energy, and further from the nucleus are higher energy. So electrons are not just flying around, they're in specific orbitals or like levels, and each level is a slightly higher energy level. Now, each orbital by size is only so big. They can only fit a certain number of electrons. And part of that's to do with the fact the electrons are negatively charged. They're all negative. They're all the same charge. They're all negative. And the electrons repel away from each other. They're attracted to the nucleus, but they repel from each other. So they can't really fit too many. Now, how do you figure out how many electrons could fit in an orbital? Well, there is one group on the periodic table. Groups go up and down. The last group is called the noble gases. Helium, neon, argon, krypton, xenon, radon. The noble gases, all of their electron orbitals are always all full. So we can always look at that. So if we look at, say, helium, Helium only has 2 electrons. It only has 1 orbital. The electron configuration, which is down here at the bottom, the electron configuration is 2. And they're both electrons are in the first orbital. Now, neon, second atom, says 2 orbitals. It has 2-8. 2 electrons fit in the first orbital, 8 electrons fit in the third. And then if we do the next one, which is argon, 2 electrons fit in the first orbital, 8 electrons can fit in the second orbital, and the third electron orbital, that's a weird one, it can fill up with 8 electrons. Okay. And then if we look at krypton, something funky happens because the third orbital's funky. It's 2-8-18-8. As it turns out, that third orbital can fill up with 8 electrons, or it can stretch and it could fill up with 18 instead. So we have for krypton 2 in the first orbital, 8 in the second orbital, 18 in the third orbital, and then 8 in the fourth orbital. And the fourth orbital can fill up with 8, or it can stretch too. The first 2 orbitals are locked, 2-8. And then the third and the rest of the orbitals can fill or stretch, and they're a little funky. Chemistry, these electrons, a long time ago, they said, what are we going to do? They didn't think you were ever going to pay attention and learn and have to think about this. So they didn't think how hard this would be. They did what they wanted to do. We just have to learn what they do. All right, this is the last slide. This is what's going to happen. In the first orbital, helium, there's just 2 electrons. And in the second orbital, we have neon as our example. It's 2-8. The first orbital is still full. Second orbital gets 8 electrons. That orbital is full. Neon has 2 orbitals. They're both full. Argon is the third atom. All 3 orbitals are filled. 2-8-8. First orbital's full. Second orbital's full. The third orbital's full. But look what happens here with krypton. Something funky. That third orbital, the purple one, stretches out, and it can stretch and fill in a bigger way. It can kind of be full at 8, or it can expand to 18. And then the fourth orbital is full, with 8. But then look what happens with xenon. Here we have full 2 in the first orbital, full 8 in the second orbital, full 18. But then that fourth orbital has stretched also, and that now has 18. And the fifth orbital is full with 8. But then watch what happens. Holy smokes. The first 2 orbitals are the same, 2-8. The third orbital is 18. That fourth orbital stretched again to 32. The fifth orbital stretched to 18. And then radon has 8 in its 6th orbital. So electron orbitals hold the electrons in an organized pattern. There's always 2 electrons in the first orbital, always 8 in the second, and then it gets a little funky. But how do you remember how many electrons could fit? The noble gases always have only full electrons. We're going to stop now. Don't forget, go on YouTube, look up the Beatles, When I'm 64. It's a really good song. When I Get Older, Losing My Hair, many years from now. Dun, da, 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 da. You're going to love this song. All right, thanks for watching. End.